graph work, we either sketch or plot values. Whether we plot or sketch values, we need Cartesian space. How can we use Cartesian space to sketch values from tables? That takes us to lesson number 3 of this book. Please join me as I use our foregoing table to demonstrate sketching values on Cartesian space. Please follow through.
Watch this table closely. It is one of the tables we have seen before. At this point, we recall that x and y have replaced the variables, making us concentrate on pure mathematics instead of real-life situations. After we saw this table, and after we derived the formula that describes the behavior of these numbers on this table, we got this equation. Don't forget, y is equal to 2x plus 5. Do you remember? I know you do. Now, let us sketch this equation on this Cartesian plane. How do we do it? As before, we have to start by calibrating the axis. First, let us notice that in this x column, which corresponds to this x-axis, there are no negative values. All the numbers here are positive. This is why, again, like before, we're not going to make use of this section. And in this y column, corresponding to this y-axis, all the values are also positive. None is negative. As a result, we are not going to make use of this down part. As usual, we magnify the use of this space for positive y and positive x. Now that we are going to use the positive space, what do we do? Let us start with the x. This is the x-axis. The highest value of that x is this 5. See where I wrote 5 here, which means the highest value is 5. That means that from here, which is 0, to this point is 5. Whatever its unit is, we don't know, because we don't know from which real-life situation this table was gotten. It remains hidden until we are informed. Then, if from here to here is 5, first, I hope you know why I wrote 5 here. I wrote 5 here. It is not possible. It is not compulsory that it must be at this point. Anywhere I like along this axis, as long as it is not on this 0, I can write my 5. I could as well have written the 5 here or here, anywhere else, but I chose to write my 5 at this point. Again, why 5? 5 because 5 is the highest value on this x, on the x column. So that is why the 5 is written here. What then will be written between 0 and 5? How do we get the values that are going to write between 0 and 5? Very simple. It depends on us. It depends on how many divisions we want to get, or how many intervals we want to get. We first ask ourselves, from this 0 to 5, how many divisions or intervals do we want? We can want any number of intervals, but we should be careful to choose the number of intervals that is practicable. From 0 to 5, we can choose to divide it into 5. That is, divide this space from here to here into 5, so that each equal space or each equal interval will be 1, 1 until we reach this 5. If we divide from here to here by 10, it means that each interval will be 0.5. I hope you know why it should be 0.5. In fact, choose a number of your choice to divide this 5. Whatever you get is number of divisions you are going to get. Now I choose to divide from here to here into 5 different intervals. That means that each interval will be equal to 1. Okay, now the next thing is that you watch how I will calibrate from this 0 to this 5, having known that each equal division or each interval corresponds to 1 unit. Let us see. See the calibration: 1, 2, 3, 4, 5. Don't forget how it was gotten. Let's do a similar thing in the case of y-axis. From this point to this point is a line that has a magnitude. That is, this straight line from here to here has a magnitude. And I chose to write 20 here. I chose to write 20 at this point. You may ask, why did I choose to write this 5 here and not 15 here? 15 could have been here. But this example is trying to highlight something. It highlights the importance of knowing that it is not compulsory that the highest value is what you write at the topmost part of the axis which you want to calibrate. In fact, know it now that anything above that highest value can be there. This is 15. It could have been 15 here, but I chose 20. It could have been 18. It could have been 16. Anything above 15. From 15 above can be here. But don't make it so far from 15 because I said anything above it can serve. So from now on, do not insist that the number that is going to serve as the highest number on the axis before the calibration of the axis is that number which is the highest value or the highest number in the table corresponding to a particular column. That I wrote 5 here is to make you know that we can start with that highest one. That I wrote 20 here is to teach you or make you understand that we can as well choose something above the highest value, but not far from 8. Therefore, don't insist that the highest value is what you have to make use of when you are trying to calibrate an axis. Now, having seen 20 here, from this point to this point is 20. Next is, how do I write values between this 0 and this 20? As before, we choose to divide this gap from here to here into any specified number. If I divide from here to here into 2, it means I will have only 2 intervals. That is 10, 10. If I divide this interval, this gap from here to here into 4, each interval will be 5. So you have 5, 10, 15, 20. If I divide this gap from here to here into 5, each gap will be 4. And that will be 4, 8, 12, 16, and 20. If I divide from here to here into 10, I will have 10 different intervals, each corresponding to 2 units. And that will be 2, 4, 6, 8, 10, 12, 14, 16, 18, and then 20. if I divide this 20 by 20, I'll have 20 intervals, and each interval will be 1 to be counted as 1, 2, 3, 4, then down to 20. Of all these options, I chose to divide this gap from here to here into 4, so that each interval will be 5 units. Let me calibrate the interval or calibrate the axis using this division. Let's see how it goes. Now, after breaking the gap from here to here into 4, we now have 5, 10, 15, and 20. Now, let us do as before. And what is it? Let us start looking for the points of intersection in this space. That is where 1 meets 7, where 2 meets 9, where 3 meets 11, where 4 meets 13, where 5 meets 15. But the question now is, though we have 1, 2, 3, 4, 5, so we can locate them on this X. It is not every value we see on this Y in this Y column that we see in this Y axis. For instance, the first value is 7, and there is no 7 written here. 7 exists somewhere between 5 and 10, but not written. This 9 is not written, but exists somewhere between 5 and 9. This 11 is not written, but exists somewhere between 10 and 15. This 13 is not written, but exists between 10 and 15. Now, the question is, if we find it easy to locate 1, 2, 3, 4, 5 on this x-axis, how do we locate 7, 9, 11, 13, and 15 on this axis? We are going to do it by approximation, but later we're going to do it with some level of precision. But for now, we stick to approximation of positions. Now, let me start with the first one, which is the x. It is assumed that all the values of x have been located by this calibration. This is a coincidence that after calibration, all the values under the x appear on the calibration. But it's also unfortunate, but exciting to learn that all the values in this y, except this 15, are not obtained seen written on this y axis. Then, what we do? Let us start with this 7. Where is this 7 exactly? It is somewhere between 5 and 10. By approximation, we can place it somewhere here. Later, we learn how to pin it down to its exact location. But for now, we make do with approximation. Let it be here. Let's see how to go about it. What about this 9? It is somewhere very close to 10. This is 10. That means 9 is somewhere very close to it here. 11 is just a short distance after 10. Then this 13 is midway between 10 and 15. That is somewhere here. This 15 is here. Let me use dots to indicate these approximated positions of these values. Now, with the dots on this axis, we propose that this 7 is here, and this 9 is here. Of course, 10 is still where it is. This 11 is here. This 13 is here. And this 15 is still where it used to be. At this point, let us start looking for partial points of intersection between the values of x and y. To start with, this 1 is here, and 7 is here. So, as usual, 7 will meet 1 somewhere here. let me draw the points of intersection to cover both this point and other points. It is believed that with the last example I gave, you know how this is going to proceed. Let me get the points of intersection. Right, this is the complete array of the partial points of intersection. We have these 5 points, 1, 2, 3, 4, 5. This corresponds to 1 against 7. This corresponds to 2 against 9. This corresponds to 3 against 11. This corresponds to 4 against 13. And this corresponds to 5 against 15. At this point, let us run the line of best fit as before. Okay, this is our line of best fit. What a beautiful line of best fit. Don't forget that this sketch is a sketch for this equation corresponding to this table. The equation says y is equal to 2x plus 5. Okay, that means that we have to write this equation y is equal to 2x plus 5 around this area to keep reminding us that this line describes that equation. Let us see. Finally, we have it here. Y is equal to 2x plus 5 describes this line.